So in this video, we're going to look at calculating signed area as a function of x, or any variable name you want to use. So in the videos that we've been working through recently, we've identified that the definite integral evaluated over a closed interval from a to b gives you the signed area under the curve from a to b. And by signed, we are indicating that if the curve is above the x-axis, we get a positive area, whereas if the curve is below the x-axis, we get a negative area. So this is what the big part of what we've been doing the last couple homework assignments has been to develop this idea of the signed area under the curve. And remember, to calculate the signed area under the curve, we integrate from a to b. And we do f of b minus f of a, where big F is any antiderivative of little f of x. And so the idea is, what if you don't know up front what the closed interval is over which you want to work? In other words, what if you want to start on the closed interval from a to question mark? I don't know what the number is I want to plug in here to close off the other end of that integral. And the idea is you could put a variable in there. You could say, hey, I'm going to integrate from a to x. So instead of going from a to b, we'll go from a to x, and then we can let x vary. Maybe I can let x be a number right here. I can let x be a number here. I can let x be a number out over here. And I can evaluate different signed areas because I'm allowed to let x vary. And that's the idea behind calculating a signed area as a function of x, is just letting x be the upper bound on that closed interval over which you're integrating, so that you can vary x to get different signed areas. So for example, if we want to find the signed area on the interval from 0 to x for underneath the cosine function, so we want to integrate from 0 to x cosine t dt, we could go ahead and come up with our function for that. So we're going to get the integral from 0 to x of cosine of t dt is going to equal any antiderivative of the cosine. And the sine function is an antiderivative of the cosine because the derivative of sine is cosine. And this would go from 0 to x. And then we could simplify this a little bit. We go sine of, we plug in that upper bound of integration, minus, by the fundamental theorem of calculus, minus the sine evaluated at the lower bound of integration. And the sine of 0 is 0, so this just simplifies to the sine of x. So it turns out then that the sine of x will tell us the area underneath the curve cosine, the cosine curve on the interval from 0 to x, where we get to let x vary. So for example here, if I want the interval from 0 to pi over 4, I can simply plug pi over 4 into the sine function. I get the sine of pi over 4 is equal to, the sine of pi over 4 is the square root of 2 over 2. And if you approximate the square root of 2 over 2 in a calculator, you get about 0.71 as the area. If instead we wanted to know the area under the curve on the interval from 0 to pi over 2, now we can just plug pi over 2 in for x. I can say, hey, what's the sine of pi over 2? Well, the sine of pi over 2 is just equal to 1. The area under the curve is 1 on the interval from 0 to pi over 2. And if I want to know the area under the curve of the cosine function on the interval from 0 to pi, I can just plug pi in for the sine function. Now the sine of pi is equal to, the sine of pi is 0. And over here in the picture you can see what's going on. Between 0 and pi over 2, the area under the curve is equal to 1. And because we have a signed area, and because the cosine function is below the input axis right here, this area is actually evaluating to -1. You can see by symmetry that these areas are the same size, but the area underneath the x-axis will be negative. So we're getting an area of 1 plus a signed area of -1, adding up to a net area of 0. So again, if you want to know the area under the curve on the interval from a to x, you just put the a and the x in as your bounds of integration using the fundamental theorem of calculus.